Let's now go over a list of terms relevant to the general trees. And we're going to use this family tree for all the examples, for exemplifying all the terms that we're going to talk about. And you can see in this family tree right away, it's non-linear because you do have a hierarchy over here formed by all the nodes over here. For example, you can see David somehow sits at the top of the hierarchy, and Shirley, Vanessa, and also Peter, they kind of sit at the bottom of the hierarchy. The way you look at the tree will be the top over here will be the root, which we're going to define in a moment. And also we said the bottom level over here will be the leaves over here. It's kind of the opposite to what your real life experience about a tree. I'll try to do a little bit of visualization just for you to see that just for once. But in computer science, whenever we talk about a tree data structure or ADT, you have to somehow put it upside down for the tree, right? You know what? Let me show you right away. Right? Because I'm going to do it just once, right? You can see this is the CS, computer science way of organizing the tree over here, right? However, of course, you can think about the way we're doing over here is kind of the opposite to the real life. In the real life, of course, you would think the root should be over here and then the tree will actually grow upwards, like it this way, right? However, in our specific context for CS, we're actually going to go for the opposite way, which will be something like this. It's going to be the root of the tree, and it's going to grow downwards, exactly like that. So in case you're confused about why this is inconsistent with what your real life experience has been for trees, that's basically just the way it is, right? Because it's just much easier for us to talk about traversal and also to define the hierarchy like above and also below, the non-linear structure. All right, that's something I want to show to you. And let's now go back. And we want to talk about the different terms. Let's start from the easy ones. So there is a top element of the tree over there, simply the top. And then it's called the root of the tree, which I already mentioned. So what will be the root of this particular family tree? Should it be Shirley, Vanessa, Peter? Somehow, because you would think the root should be at the bottom, right? But apparently they should be not. That should be the top element by definition. There's only a unique root for every tree. You cannot have more than one roots. So in this case, it will be David, right? So let me just annotate it. It's very important to know we have only a single unique root of the tree. So this is the root for every tree. Is not only that single, it's also unique. You cannot have more than one. You cannot have more than one root. Of course, in the case where the tree is simply empty, in that case, you simply don't have any nodes, including that you don't have any root. That will be some special case I'll talk about when I talk about the general definition for the general trees. I'll get there a little bit later. All right, so that's for the root. And let's see the next one. And that will be the nodes immediately above node n. So here the n can be any of the nodes over here. So I'm talking about the general definition. So I'm going to give you several examples. If you choose to know Elsa, for example, or if you choose to know David, or if you choose to know Shirley, you may have different answer, right? So that's what I meant by n over here. It's more like a placeholder for some node, in which case you can substitute it by any node in the tree. And we can actually get a parent of n. So the parent is defined as the node immediately above, not just above, but immediately above, right? So one example will be, what will be the parent for Vanessa? In that case, immediately above will be Elsa, right? Let's talk about it. So now let's talk about, let's say, for example, if I simply circle Vanessa, so Vanessa is the node we're talking about. In that case, Elsa will be Vanessa's parents over here, right? If I fix it, so this will be the parents, right? What if I want to actually fix Elsa over here? Who will be Elsa's parents in this case? Elsa over here. In that case, Chris will be Elsa's parents. So it seems like parents is also unique. There's only one parent. Of course, in real life, we have two parents. But in the case of the tree, we got only one parents. So this will be the parents. Again, the parents will be single and also unique. All right, so every node has exactly one parent in the tree. However, there's one exception, which I'm going to point out to you. What about the root of the tree? In the case of David, you don't really have any nodes immediately above the tree, immediately above the root, because the root is already a top element. There's no node that's going to be above the top, right? So in this case, this is the only node without a parents. Or programmatically, you can think about the parent would just be null. All right. Alrighty, so that's pretty straightforward. Let's now move on. Oh, let me just say one more thing. Here. So when we say Elsa is parents of Vanessa, right? Of course, you can also say Elsa is the parents of also Shirley, and Elsa is also the parents of Peter, because Elsa is immediately above these three nodes. And you can see exactly the line over here that suggests the immediately above notion. Okay, and we say that Chris is parents of Elsa. By these two, you cannot, what can you say if you simply say, in that case, Chris is parents of Vanessa? That's something I'd like to clarify right away. This might be one of the common mistake that beginners of the tree might actually make. It seems like we say x larger than y and also z larger than y. So can we conclude that z is larger than x? The answer is transitivity is not going to work for parents, right? So when you say Chris is also a parent of Vanessa, this conclusion over here is simply false, right? It's not the case. Because according to our definition, parent has to be immediately above. However, what will be right is something we call ancestor, which I'll get into later. Right? Just remember, for the parent, it has a very strict definition. It has to be strictly above, right? Immediately above. Right, the next one. What symmetrically, all the nodes immediately below a particular node n, it will be the children of n, right? And be very careful over here. So here I say for the parents, I would say the node. So that means it's a single one and also it's unique. On the other hand, when I say the children over here, I simply say all the nodes over here. So all the nodes over here kind of suggest it could be 0, it could be 1, it can be more than 1. Let's see example right away, right? In that case, you can see since Vanessa is actually since Elsa is actually the parents of Vanessa, symmetrically we can say Vanessa is one of the children of Elsa, right? So we can say it's a child as well. I can put child. Right? Similarly, you can think about Peter over here is also one of the children of Elsa. And Shirley also is one of the children of Elsa. Right? Let's see some special case over here. You can see for Chris, how many children does Chris have? According to the family tree, it's going to be Elsa and also Anna, right? You can think about for Chris over here, the number of children is actually 2. Elsa and Anna, right? What about the number of children for, let's say this one, for Ernesto over here? Ernesto, you can see there is no nodes immediately below Ernesto. So by definition, Ernesto has no children. And we actually also got a special term for that, which we'll get into later. The number of children over here is simply 0. Right? And by the way, I can mention that right away. We call this kind of nodes either external node, or we simply say it's a leaf. I think the leaf here is a little bit symmetric. It's a little bit analogous to what you will see in real life. It's like the far end, the boundary of a particular tree, right? Because you cannot really branch it out any further, right? So whenever you got some node which can branch out, it wouldn't be the leaf. But if you got a node like this, it's the leaf because you cannot branch out any further, right? It's kind of the analogy that we are using. Okay, and we got so that's about children, that which I already mentioned. Right? You can see for the case of the Ernesto, he simply doesn't have any children. So we'll just say just empty. I'm just saying that the children is more like a set concept. It can be empty set, it can be a singleton set, or it can be a set containing more than one child nodes. All right, let's now try to move further for other terms. Okay? We also talk about it's going to be, let's say for a particular node n, we're going to start by unioning. We can take the union of n itself, and also the parents of n, and also n's parents' parents, and also n's parents' parents, all the way until the root. So what does that mean? So these will actually collectively call the ancestor for the n, right? It's rather easy. Let's see. Over here. Let's say we have this. Let's say we start from, let's say Shirley over here. So Shirley herself will be included as in the ancestor. Also, Shirley's parents will be Elsa. And Shirley's grandparents will be Elsa's parents, which will be Chris. And then we simply follow this particular path all the way until the root. So the green one over here is so-called ancestor. Okay, so ancestor of Shirley over here is going to contain Shirley itself, Shirley herself, and also Elsa, and also Chris, and also all the way until the root of the tree, which will be David. And just remember, you always include the node itself. So a node is also its ancestor at the same time, right? And you can also think about what will be the ancestor for Ernesto. It will be Ernesto himself all the way until David. What about the ancestor for Vanessa? It will be Vanessa herself, parents, Elsa, grandparents, Chris, great-grandparents, David. So these will be the ancestor for Vanessa, right? You got an idea. And a little bit look ahead. The path in which we try to look for all the ancestor, this particular path over here is called ancestor path, which we'll also talk about in the later terminology. Okay. And symmetrically, we also got something called descendants, right? Kind of the opposite direction. So it's going to be the union of the node itself and also children and also children's children, which would be grandchildren, right? We call them. We call this union would be the descendants, right? Let's now take a look at some example. What about descendant for Vanessa, right? By definition, descendants for Vanessa would be Vanessa herself and also her children. But according to the family tree, Vanessa does not have any children. So the descendants for Vanessa will only include herself, right? In this case. What about the descendants of Elsa over here, right? Let's now try to take a look. Let me use the pink over here. Let me use the pink over here. Well, who will be the descendants of Elsa? It will be Elsa herself and also her children, which will include Shirley and also Vanessa and also Peter over here. So these are the four nodes over here, right? So you can, I'll put it here. So descendants of Elsa includes Elsa herself and children, and also Vanessa, and also Peter, right? And notice that a node is simply its descendants at the same time, right? So that would mean over here. Let me just talk about Elsa over here. We know that Elsa's descendants will be Elsa herself and also all the children. This will be descendants over here, right? What about Elsa's ancestor? A pop quiz. What will be Elsa's ancestor? In that case, that will be Elsa herself, Chris, all the way to David, the root, right? So a node will be their ancestor and also descendants at the same time, right? That's something also written in the slide by definition. Okay, which nodes in the tree has the most number of descendants? That should be quite easy to see. That means the higher the higher you are in the hierarchy of the tree, the more descendants you should have. In that case, it will simply just be the root. And what will be the descendants for the root? You will basically the root itself, and also children at the first level, children's children at the second level, and also children's children's children at the third level. So that'll be the entire tree over here, right? So let me just write this one. It's also a special case, David, over here. Okay, let's see. Descendants of the root covers the entire tree. All right, let's now move back. All right, so that's the remark I just mentioned before. By definition, a node is both its ancestor and descendant at the same time. Just don't forget, right? If you were asked to really to include the ancestor for a particular node, it definitely should really include its itself. Also similarly for descendants. Let's move on. And the next one will be, given some node n, which can be replaced by any of the node in the tree, there are other nodes that might have the same parents as node n that we are talking about. Let's see the example right away, but they are called the siblings of this particular node. Let's see from our diagram over here. Right, so for example, you can see for Vanessa, we know that her parent is Elsa. Do we have any other nodes who also have the same parents, Elsa? Yes, we do. In that case, Peter and also Shirley, we actually got two siblings for Vanessa. You can say they're siblings of each other, right? So there's very natural concept over here. So you can think about this part over here. I'm gonna box Peter, Vanessa, and Shirley. You might be wondering, given that these three nodes are siblings, do we have any notion about which node might be elder and which one might be younger? We don't really have the notion about elder versus younger in the case of the tree terminology, but we do have a notion about which node may actually have to come before other nodes. In that case, it's called an order tree. So just keep that in mind. We're going to talk about that particular terminology a little bit later. But there's certainly no notion about younger versus older, unless you want to define that for your own tree. Okay, so these nodes are called the siblings because all these nodes have the same parents. Or think about Elsa's children are exactly these three nodes, right? Just quickly, how many siblings does Elsa have? Well, in this case, only Anna, right? You can see Elsa and Anna, they have the same parents, Chris. How many siblings does Chris have? In that case, Ernesto. In that case, just one, right? How many siblings does David have? In this case, none, because David does not really have a parents, because David is already the root by definition.